All right. So we have we're into our third unit, which is we did kinetics, we did thermochem 1, and we did thermochem 2. We might finish today. We talked about the first law and the second law of thermodynamics so far. The first law was about the law of conservation of energy, and we just said that in a chemical reaction, energy is conserved, so you can convert potential energy to thermal energy and work and so on, but you can't make energy disappear or appear out of nowhere. We also looked at the second law, and that's kind of what we dealt with mostly last class. And the second law was really about whether reactions were spontaneous or not, and what conditions need to be met for a reaction to be spontaneous. And what we arrived at was that the delta S of the universe had to be positive in a spontaneous process. And that's a statement of the second law. And the delta S of the universe is really equal to the delta S of the system plus the delta S of the surroundings. So you can have a system with a negative delta S as long as the delta S of the surroundings was large enough positive to make the sum a positive value in a spontaneous process. So that was all fine, except we had to figure out then how you can calculate the delta S of the system and the surroundings. And we said that for the surroundings, we're going to say that the delta S of the surroundings is just a function of the delta H of the reaction. You know, because if heat is given off to the surroundings, we're assuming the surroundings aren't experiencing chemical change. So they absorb heat from the system. That's going to cause the delta H of the surroundings to go up. If they provide heat to the reaction, if it's endothermic, then the delta H of the delta S of the surroundings is negative, goes down. Then we wanted to look at how you found out what the delta S of the system is, which is a little bit more tricky. We said you can just use delta H over T if it's a reversible process, like a phase change. But in many examples, that's not the case. So that's kind of where we stopped. We didn't really have yet a good or complete way of calculating the delta S of a system, only the surroundings. So this is where the third law of thermodynamics comes in. And the third law of thermodynamics allows us, it provides us sort of a starting point from which we can calculate the delta S of a system. Then we put the system and the surroundings together, and then we have the universe, and then we can figure out if a process is spontaneous or not. So the third law of thermodynamics just says a perfect crystal has zero entropy when it's at absolute zero. So when you're at absolute zero, we say its thermal energy is a minimum. It's the lowest possible value. The motion, there is some vibrational motion still at 0 degrees Kelvin, but it's again at a minimum possible. And perfect crystal just means that there's no flaws or defects, that every atom or molecule in that crystal is perfectly arranged and perfectly aligned. There's none that are out of place. If all of those are met, we say that the system has zero entropy. In other words, another way of saying that is that this system has one microstate. There's only one way to arrange those atoms and that energy in the crystal in that specific orientation, which is the orientation that it's at. So this is nice because it tells us the absolute entropy of that system is zero. This isn't delta S. This is the absolute entropy of that system is equal to zero, which is a great starting point, which we cannot do for things like enthalpy, but we can for entropy. So the idea then is if we know we have a crystalline solid at 0 Kelvin, we know that at that point, our entropy is equal to 0. What we can then do is figure out what the entropy of any substance or that substance might be after you warm it up. So let's say we take that solid crystal at 0 degrees K. We're starting with entropy equals 0. And what we want to do is just warm it up to its melting point, which is this step 1. we have an equation, which I'm not going to get you guys to use or calculate. Uses a bit of a calculus there, some integration. And what you can do is figure out what the entropy change is, bringing it from 0K up to its melting point. So that what that allows us to do is calculate the entropy after that warming. Then we know what we're doing is once you hit the melting point, adding more heat is going to cause it to melt into a liquid. And we know what the delta S is for melting it. We've done that one last class. Then we continue to warm that liquid up to the boiling point. We have another equation which we can calculate the entropy change associated with that warming. Then we have another equation for the entropy change associated with vaporization. And finally, we continue warming it. We have an equation for the delta S of warming it once it's a vapor. So essentially what we're doing here is we're starting at 0, and then we go through these different phases of heating, phase change, heating, phase change, heating, phase change. So at any temperature, you can figure out what the S is, what the entropy value is for that substance. So let's say you had that substance at 200, let's say you're at like 25 degrees Celsius and it's water. Well, we know that's liquid. We're probably right about here. And you can run that calculation and figure out what the absolute entropy is for water at that temperature. All right, my computer tried to update, go away. So we call this the standard molar entropy. The standard molar entropy is the entropy of a substance at 298 Kelvin or 25 degrees Celsius in its standard state, whatever its state is at that temperature, whether it's solid, liquid, or gas. And we can calculate these for really anything. And we can only do this because we have this starting point, which is given to us by the third law. So here's an example of some standard molar entropies. Again, these are like heat enthalpies of formation, where these have been measured and tabulated for many substances. When I say measured, I mean calculated. And you can find online, you can find tables of these. The CRC handbook of chemistry and physics would have long lists of these things. And there's some interesting things you can see here. First of all, you can see that carbon comes in two forms. Carbon has two allotropes. Well, it's got more than two, but there's two that are listed here, diamond and graphite. And you can see that diamond has a lower standard entropy value than graphite does. So what that suggests is that the diamond has fewer microstates. And that's something you often see when you have a substance that's more crystalline. You can see water. We have water as ice as a number of 45. Water as a liquid is almost 70. And water as a vapor is 188.8. So this is the same substance at the same temperature in three different phases. So what you can see here is that the solid form has the lowest entropy, and that turning it from the solid to the liquid increases the entropy, and going from liquid to the gas increases the entropy once more. Generally speaking, this is not generally speaking, this is always the case, liquids of a given substance will have a higher entropy, higher standard molar entropy than the solid of the same substance, and the gas will be higher than either one of the two. And we talked about this last class in terms of why gases have higher entropy. They occupy a higher volume. There's more possible microstates. There's more energy in the system. And that's that. Anything else of interest here? Not really, except maybe to point out that the standard molar entropy gets larger the more atoms there are in the molecule. If you take something small like water and compare it to something large like octane, both are liquids. There's a big difference there in the standard molar entropy. So as you increase the number of bonds, as you increase the, you might say the flexibility of the molecule as well, the entropy of that can increase. Great. So we have these standard molar entropies brought to us courtesy of the third law of thermodynamics. And what we can do with these is calculate the delta S for any reaction using the same process we've already learned using enthalpies of formation. So it's just this, the delta S for a reaction is just going to be the sum of all the standard molar entropies for the products, subtract all the standard molar entropies for the reactants. It's identical to the equation we've already seen for delta H. That equals the sum of the delta H of formation for the products minus the sum of the delta H of formation, 0 to 98 of the reactants. So if you already know how to calculate delta H using enthalpies of formation, calculating delta S, exact same thing, except we're using standard molar entropies, which again have been calculated and put in a table for us just to use. So this is great because any chemical system, any reaction that's undergoing, any kind of chemical system that's undergoing a reaction, we can calculate what the delta S and the delta H for that is just using already measured values in a table, which is good, makes our life easy. Great. Calculate the standard entropy change for the melting of an ice cube at 298 K. So it's 25 degrees, put an ice cube on the bench top here, it will eventually melt. This reaction, if you wanted to write it out like a reaction, would look like this. Solid goes to H2O liquid. So all we need to do is to calculate the delta S of reaction at 298. It's not really a reaction per se here, it's more of a phase change, but you can write it out this way anyway. It's the sum of the delta, so sum of the standard molar entropies of the products, which is water liquid, and there's only one reactant, which is ice. And that will equal to, do this in my head, 24. Okay, so that would be the delta S of fusion in this case. Notice the value is positive, which we expect going from solid to liquid. Should have a positive delta S. We're going from a phase change to closer to the gas phase. Here's another one. It says calculate the standard molar entropy change. Let me just find my numbers here. Great. Calculate the standard entropy change for the combustion of methane at 298 K. So what we need to begin with here is a balanced equation, which is not provided. So that's going to look like CH4 gas plus O2 gas goes to H2O gas plus CO2 gas. And we have to balance this thing, so we have 2 waters, and that's going to give us 2 O2. That should be a balanced equation right there. Okay, good. So then what we need to do is just add up the sum of all of the delta S for the products. So what that means is we have 2 waters, and the value for water is 188. Plus the other product, which is CO2, 213.7 joules per k-mole, minus, on the reactant side, we have methane, plus 2 times O2. You know what the units are there, joules per k-mole. And when you calculate this out, you get negative 5.2 joules per k-mole. All right, now looking at this, does this value make sense? I guess first of all, looking at the balanced equation that you see up here, just looking at that equation, how do you predict if delta S for that reaction is going to be positive, negative, or close to zero? What you'd want to do is look at the change in the moles of gas. If it's generating gas, then it's definitely going to be a positive delta S. If it's consuming gas, number of gas molecules goes down, it'll have a negative delta S. And if you have the same number of moles of gas on each side of the equation, you expect a delta S value that's going to be small, could be positive, could be negative, but it's probably going to be pretty close to zero. And that's what it kind of looks like we see here. 5.2 is not very large in relation to any of the numbers of the individual substances in the reaction. And if you count the number of moles of gas here, we have 3 on the left, 3 on the right. So this actually makes sense. We're not really expecting a large positive or a large negative value for delta S. So we have a number that's very small, close to zero, and that's it. Another thing I just wanted to point out here as well is notice that oxygen is there, and oxygen has a nice big fat standard molar entropy, 205.1, and pure substances, if you remember when we did enthalpies of formation, pure substances in their standard states like O2 had values of 0 for standard molar entropy. No, for enthalpy of formation. That is not true for standard molar entropies. No substance has a value of standard molar entropy of 0 at 298. None of them. So everything is going to be some positive value. If it's a gas, it's going to be especially large. If it's solid, it's going to be a little bit less. Yeah. Perfect. Okay, so I think now we're ready to fully deploy the second law of thermodynamics because we know how to calculate the delta S of the surroundings, and we now know, using enthalpies, standard molar entropies, how to calculate delta S of the system. If we put the two together, then we can then figure out the delta S of the universe. So let's look at a reaction. Here we have hydrogen gas plus half a mole of oxygen gas goes to water liquid. First question, do we expect delta S of the system to be positive or negative? And this is not looking up any numbers or doing any calculations. This is strictly just looking at this balanced equation. And to answer this, we have to count the moles of gas. And we see we have 3, or actually 1.5 moles of gas on the left side, 0 moles of gas on the right. So we would say delta N here is negative 1.5. That means this is definitely going to have a negative delta S. Okay, because the number of gas molecules goes down. All right, let's calculate it. We have delta S of this reaction is going to be equal to the sum of the standard molar entropies of the products minus the standard molar entropies of the reactants. We can get all these numbers out of a table. And when we do the math, we get this value for delta S system, capital S, negative 163.4 joules per k-mole. So that makes sense. That matches our expectations before that it's going to have a negative delta S value. And that's the delta S of the system, the delta S of the reaction. Now we have to consider as well, because just looking at the system alone, you might predict this reaction to be not spontaneous, because we need a positive delta S universe. but we only have one part, right? Because delta S universe is the sum of the delta S of the system plus the delta S of the surroundings. So we have this value, negative 163.4 joules per K mole. Now we need to calculate the delta S of the surroundings. We can do that, no problem. The delta S of the surroundings, we know, is the delta H of the reaction divided by T. How do you get the delta H of this reaction? Delta H of the reaction you can get a couple of ways. You can use a calorimeter and measure it, or you can use the enthalpies of formation and calculate it. Or you can use that, get an estimate at least using the bond dissociation energy method. So we have a couple of methods to get delta H. This is the value of delta H. You take that number, divide by K, and you get this value, positive number, for the delta S of the surroundings. That number is quite large, positive 959.1 joules per K. This is because this energy is giving off a lot of heat. So that's absorbed by the surroundings. Surroundings are absorbing energy, so they're going to have a positive delta S. All right, so we know if the sum of the delta S of the system and the delta S of the surroundings is greater than 0, this will be a spontaneous reaction. Let's take our numbers. This is what we see. We have a value for our delta S of system, delta S surroundings. The sum is a nice big positive value. So because this is positive, we would expect this reaction to be spontaneous. It doesn't mean it happens without being initiated, so you might need to provide a little bit of activation energy at the beginning to get it started. But once it gets started, the reaction will proceed, and the energy that it gives off will be enough to produce the product. Cool. It's a nice example of a reaction with a negative delta S for the reaction, yet it's still spontaneous because of the delta S of the surroundings part. Okay, I've heard arguments actually people have made before against evolution, and the arguments were sort of centered around the idea that, you know, having matter on Earth organize itself into human beings, which we, you know, I guess the entropy change with that would be very negative. They'd say that's impossible because of the second law, that spontaneous processes decrease entropy. But they're only looking at the delta S of the system and not the delta S of the surroundings, because the rest of the universe, like the sun, there's a huge, crazy increase in entropy of the sun associated with it giving off light and energy, which we absorb, and it's that energy from the sun that we get that allows for life and other processes on Earth. So, you know, if you're looking at entropy, trying to determine if something is likely to take place or not, you can't just take a small piece of the universe and forget about everything else. That the spontaneity depends on both the system and the surroundings, and you can have an increase or decrease in entropy of a system and still have that reaction be spontaneous, depending on what's going on in the surroundings. Cool. Now, there's another way of looking at this. It's essentially the same thing. It's another way of applying the second law. And this is a much more common way that people use to apply the second law, whether they know they're doing it or not. And it's using a type of energy that we call Gibbs energy. And Gibbs energy is a form of energy that has, I'll put it this way, it's what it actually means has much more importance, and in the context is easier to understand if you're looking at a system that is doing work, like an engine. And in that context, what Gibbs energy is defined as is the maximum amount of work that you can get out of a particular system. So we're generally not as worried, at least at this point, in work being done. Yet Gibbs energy is something that is still very important, and it's something that we can apply to a number of situations like equilibrium, like electrochemistry, as we'll do in a bit. And basically what this energy tells us is whether a reaction is going to be spontaneous or not. Okay, you can think of it as like Gibbs energy is like the driving force for a chemical reaction that takes into account both the enthalpy change and the entropy change. And you can almost look at it like this, the delta H part, the equation for Gibbs energy is delta G is delta H for a reaction minus T delta S for the reaction as well. What this does is it takes the delta H, which is really, it's the enthalpy change of the system, but it's related to the entropy change of the surroundings. Because that energy associated with enthalpy, the heat that's being absorbed or emitted, goes into or comes from the surroundings, which will change the delta S of the surroundings. And then we have this other piece, which is in terms of the delta S of the system. So we kind of have the delta S surroundings part and the delta S system part, just like the second law. So you can say that this Gibbs equation that we have right here is really another expression of the second law of thermodynamics. It also brings into temperature something that we know is that as the temperature gets higher, the entropy component becomes more important. And we can see that directly in this equation. So this just says then that the delta G for a reaction, the change in Gibbs energy, or change in driving force for the reaction, or I should say the actual driving force of this reaction, it's a function of the delta H of the reaction and the delta S of the reaction multiplied by temperature. And what we find is that if you have a chemical system, delta G is a negative value. After you calculate that out, we know that that process is going to be spontaneous. If delta G is a positive number, we know it's going to be non-spontaneous. And if delta G is 0, then it's neither spontaneous nor non-spontaneous. And that kind of a situation, as we'll look at in more detail later, we would say that would be at equilibrium. Cool. So these are the rules. Spontaneous reaction has delta G negative, and you can calculate delta G if you know delta H and delta S in temperature for a reaction just using this equation that we have right here. Basically what this is saying is, a reaction could be spontaneous at one temperature, but not another temperature. And this maybe is a nice example where we talked about water freezing. We know that if you're below 0 degrees Celsius at one temperature, water turning solid is spontaneous, whereas if you are at, say, 50 degrees Celsius, the reverse process is spontaneous. So temperature is important. And the delta H is more or less the same at two different temperatures. What actually changes is the T delta S part. So at higher temperatures, the entropy part becomes more important. And in this case, the delta H, in this example, the delta H is the major contributor. Over here, the delta S is the major contributor. So temperature really does matter, and you can switch a reaction from being spontaneous to non-spontaneous by changing the temperature. Generally speaking, entropy is more important at high temperatures, becomes dominant at very, very high temperatures. You can imagine a point in time, if you go thousands of degrees, delta H almost is irrelevant. Great. So yeah, this is just my example of freezing, where water will freeze at one temperature, but not another. One other thing that we can actually look at with Gibbs energy is this idea then that we can predict if a reaction is going to be spontaneous or not, just by looking at the delta H and delta S. And if you think about it, remember, delta G equals delta H minus T delta S. We need delta G to be negative for this reaction to be spontaneous. So if delta H is negative and delta S is positive, At every temperature, the sum of those is going to be negative, and you're going to have a negative delta G. So we could say that when delta H is a negative value, and which is this situation, and delta S is a positive value, always spontaneous, pardon me, you'll always have a delta G that's negative. We would say that's always a spontaneous reaction. We could also say that if you have an endothermic reaction with a positive delta H and a delta S that's negative, we would say that's never spontaneous. So never spontaneous reactions just means the reaction would never proceed on its own towards products. It doesn't mean it won't happen or can't happen. It just means we would need to couple that reaction, that system, with some other driving force. Kind of like at the beginning of the last unit, we talked about skiing downhill. You know, gravity will spontaneously pull you down, but gravity will not spontaneously pull you up the mountain. Doesn't mean you can't get up the mountain. It just means you need to couple your motion up the mountain with some other process like a ski lift. So you can drive non-spontaneous reactions by putting in some external energy or some external force, like maybe connecting it to a battery or something like that, and providing that kind of energy to make it go. Then we have these other situations here and here where whether the reaction is spontaneous or not will depend on the temperature. You know, it can be spontaneous at high temperatures or spontaneous at low temperatures, depending on the relative values of delta H and delta S. That's where T becomes important in those cases. All right, for the following reaction, calculate delta G at 298. Okay, so this one is going to be applying this equation that we just found. And in order to do so, what we need to get is, first of all, the delta H of reaction, and second of all, the delta S of reaction. The delta H is going to be equal to the sum of the heats of formation or enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. The products, we see we have iron solid, which is a pure element in its standard state. It has a delta H of formation of 0. And I guess that's multiplied by 4. But 4 times 0 is still 0. Plus, we have CO2. We have 3 CO2s times negative 393.5. And that's in units of kilojoules per mole. Those are the products minus reactants. We have carbon there, which is, again, a pure element in its standard state, which is 3 times 0, plus the iron oxide is 2 times negative 824.2 kilojoules per mole. And that equals positive 467.9 kilojoules per mole. All right. Now we need to calculate the delta S of reaction at 298. And that's going to be the sum of the standard molar entropies for the products, which is for iron 4 times 27.3 joules per kmol, plus 3 times CO2. CO2 is a lot larger than it is for iron because CO2 is a gas. 213.7 joules per kmol. Minus, for the reactants, we have for iron oxide, 2 times 87.4 joules per kmol. Plus, for carbon, 3 times 5.70 joules per kmol. And we can calculate the delta S of this reaction then as being plus 558.4 joules per kmol. So now we can calculate delta G. and that's going to be delta H of reaction minus T delta S reaction. And 298's the temp. That's just equal to positive 467.9. Actually, I'm going to change that to joules because we need our units for delta H and delta S to match. They need to be both in joules or both in kilojoules. So let's change that to joules. Minus, the temperature is 298 K. You can tell because that's what it's looking for right there. And positive 558.4 joules per K mole. And the value you get for delta G using this is positive 302 joules per mole, which is positive 302 kilojoules per mole. Did I see a question? No, I thought something popped in front of my screen there for a sec. Okay, so what does this tell you? This reaction is a very important chemical reaction. This is how we get iron. This is how the Iron Age started. People took charcoal, carbon, reacted it with iron oxide, and heated them together, and it produced CO2, and it produced iron metal, metallic iron, which then they could use to make, I don't know, swords and stuff like that. This reaction has a positive delta G, though. Does that mean spontaneous or not spontaneous? I mean, not spontaneous, right? But how are they able to make iron using this method? Well, the answer to that question is they didn't do it at 298 Kelvin. That's room temp. If you mix these things together at room temp, nothing's going to happen, even if you initiate the reaction. So what they had to do was do this at a very high temperature. Okay, back in the Iron Age, they would heat it up very, very hot, then mix them. And what happens is if you look at this reaction, the delta H part is a positive number. The delta S part, if you add them together, because delta S is positive here, that's going to bring down the delta G, right? It's going to make it negative. So there will be a temperature at which the entropy part is more important than the enthalpy part for this reaction, and then the reaction will become spontaneous. So to make this spontaneous, you just got to bring it up to whatever that temperature is to calculate. As we will see in this example, at what temperature does the reaction become spontaneous? Well, we know the delta S is equal to positive 558.4 joules per K mole. And we know the delta H is equal to 467,900 joules per mole K. So what we just need to do is use our delta G, delta H minus T delta S, and assume that when delta G becomes 0, we're on the cusp of this being spontaneous or not. That any temperature is higher than the temperature required to bring delta G to 0 will be spontaneous. Any temperatures below that will be non-spontaneous. So set this to 0, that's our dividing line. We have delta H equals T delta S. And we would say that T is just delta H over delta S, which is 467,900 joules per mole, divided by plus 558.4 joules per mole K, which conveniently will end up giving us a number that's in units of Kelvin, which is great because what we want is a temperature. And doing this calculation, the temperature we get is 838 Kelvin. So what we would say is if the temperature is higher than 838, the reaction is spontaneous. If the reaction is lower than this, the reaction is non-spontaneous. And it turns out fire, if you're burning wood, that's a little hotter than that, depending on exactly what you're burning, what type of wood, how much oxygen, all these sorts of things. Yeah, we can predict that this reaction is going to be spontaneous at a certain point. Cool. One other way we can calculate delta G's for reactions is, we have standard molar entropies in a table. We have enthalpies of formation in a table. There's also something called standard Gibbs energies of formations that are again in a table. And if you can get your hands on delta G's of formation, then this becomes actually quite straightforward. You just need to use the equation delta R, delta G at 298 is equal to delta F, G of the products, minus the delta G of formation of the reactants. Now, you can do it this way. I will say that this information is not nearly as valuable as the delta H and the delta S that you find in tables. And the reason is that the delta H and the delta S values will change a little bit when you change the temperature, but not maybe that dramatically. Delta G's, though, change a crazy amount when you change the temperature because temperature is built into that equation you use to calculate delta G. So these values are only good at 298, and if you're at any other temperature, these delta G's of formation are totally useless. So you can calculate a delta G of a reaction if it's taking place at 298, but beyond that, there's no value in those numbers. So let's say you had a chemical reaction that was going on in your body, like an enzymatic reaction or something like that, and you wanted to know if it was spontaneous or not, what the delta G was. You can't use these numbers because these are not at body temperature. These are 298. You could, though, use the delta H and delta S values that you found in a table using the enthalpies of formation, standard molar entropies. Even though those are measured at 298, they're probably not going to be that different, 12 degrees warmer, where that's not true for these Gibbs energies. Don't use these Gibbs energies at any other temperature except for the temperature they're defined at. And I guess that's also true of the other ones if you want to be like rigorously accurate, but they don't vary near as much. Yeah, so then once you have these values, you can find it. You can predict using these numbers whether a reaction will be spontaneous or not, at 298 at least, without actually doing the chemical equation. So this is sort of the value, is that any chemical equation you can dream up. You can, without having to even go in the lab and test it, see if the reaction works or will happen, you can just do this quick calculation using numbers you find in a table to see if this is even remotely feasible before you even start. And if the delta G is calculated and it's a big positive value, you might want to rethink what you're trying to do. Find delta G of reaction for the following using the values out of this table. This will only work at 298 Kelvin, but let's do it. Delta RG 298 equals the sum of the delta G's of formation for the products, which is 2 times whatever the number is for NO2, which is in the table here, 51.3 kilojoules per mole, minus the same thing for the reactants, which is 97.9 kilojoules per mole. And if you do the math here, the number you arrive at is plus 4.70 kilojoules per mole. Positive means not spontaneous. Okay, so that means this reaction will not proceed spontaneously in the forward direction if you had a system that had equal amounts of all these substances in there. So yeah, if you mix 1 mole of N2O4 and the same 1 mole of NO2 and let it go, it's not going to proceed spontaneously in the forward direction. In fact, we might even predict it'll proceed spontaneously in the reverse direction. And we'll be looking at this sort of situation in a little more detail in, I think, the next unit, which I think is at equilibrium, which will be kind of coming up next. But this idea, I think you have already looked at equilibrium from the perspective of acid-base chemistry. We will be coming back to that, maybe not so much with acid bases, but we will be applying what we learned in the last 2 chapters with delta G, delta H, delta S, all this thermodynamic stuff to the situation of equilibrium. Lots of fun. So thank you all for bearing with me. This, I'll give you a personal opinion here. This part of chemistry, I would say, is not my, not what I would consider the most exciting area of chemistry, but I'm more of an organic guy myself, which we'll do towards the end of the chapter, end of the course, I mean. But hey, it's important, and yeah, you use it everywhere. It's a fundamental foundation of all chemical reactions. Will they happen? Will they not happen? And that and the kinetics chapter, which answered the question, okay, it happens, how fast does it happen, are really the 2 most fundamental questions you can ask about a chemical equation. Will it happen? Why does it happen? And if so, how fast will that take place? And we realize the answer isn't super straightforward. It's somewhat complex. It depends on temperature, depends on whether it's exothermic or endothermic, and it depends on the entropy change of the reaction, which is a function of things like, you know, how many moles of gas are formed or removed, how many microstates are there, and it gets pretty kind of hairy. Although the nice thing about it is that we can make measurements, we can apply math to this and come to actual predictions using mathematical equations, which is really arguably the purpose of physics, is to describe our reality using mathematical equations. I'm going to leave it there. We're done for this unit, and we will, I guess, come back Friday with another new unit. So yeah, I will be posting. Today is Wednesday. Yeah, your next assignment gets posted today, which will be on this unit. The quiz is still live and open. And the other thing I'm going to do is just make sure that we're up to date on Acorn with recorded lectures. I think I got the first bunch posted, but I don't have them all up yet. I am going to post all the remaining ones. My issue is I didn't record number 7, so I needed to find the time to re-record class 7, which I'll be able to do this morning. So that will be all up to date by the end of the day. And that's it. Is the assignment due on Tuesday, even though we don't have class? I didn't even think of that. Do you want me to make it Thursday? Doesn't matter to me. I'll change the due date next week to Thursday since we don't have class on Tuesday. People are cool with that. Great. Anything else? Are we all good? Wonderful. No problem. So yeah, we'll see you all on Friday morning.